In this chapter, we want to look at two concepts. Firstly, limits, and after that, continuity. We are in fact revisiting this concept called limits that we learned in previous years. To start with, let us look at the function f(x) equals to x squared minus 1 over x minus 1. You want to actually note that in this case, this function, it is actually undefined at the value x equals to 1. Even so, we can still study how this function behaves as x tends to 1. And to do this, let us fill in the values in this table. You want to notice that the x values here, the x values here actually approach the value 1. So from 0.9 to 0.99, 0.999. And on the other side, you can see these numbers are coming very, very close to 1. So to study how the function behaves as x tends towards 1, what you need to do is to put in these x values into the function itself. I can compute the values of the function at these values of x because they are alright. However, at the point 1 itself, the function is actually undefined. So judging from the values you have obtained from this table, you will realize that actually when x approaches 1, whether from the left or when x approaches 1 from the right, you find that the function value actually goes very close to 2. Can you see? 1.9, 1.99, 1.999. Likewise, 2.1, 2.01, and 2.001. So these values go very, very close to 2 as x goes very close to the value of 1. And we write limit x approaches 1, the function f(x) approaches the value 2. Now it can be quite misleading to see the equal sign here. In this case, this equal sign does not necessarily mean that the function f(x) is equal to 2. This entire statement basically says when x approaches 1, f(x) approaches 2. That's what this statement says. f(x) itself at the point in question, f(x) itself need not be defined and its potential need not be 2. So this statement itself only means that the function f(x) approaches 2. So this equality must be carefully read. It doesn't mean that f(x) equals to 2. It only says that when x goes towards 1, the function f(x) goes towards 2. Of course, f(x) could potentially have been 2 itself. But this is not what the statement is trying to say. This statement is trying to say that f(x) will approach 2 as x approaches 1. Okay, now so even when the function is not defined at 1, you find that actually we can still study how it behaves very near to 1 and actually can come to a conclusion that the function actually goes very close to, say, a number 2. In this particular example, because this statement is true both from the left, that is when x approaches 1 from the left and when x approaches 1 from the right, we say that this limit is so-called a two-sided limit. From the earlier discussion, using the function f(x) equals to x squared minus 1 over x minus 1, now we want to put in formal statement the definition of what is called the limit of a function. And it reads, for the point A element of the set of real numbers, a function f defined on an open interval containing A. And I want you to note this remark, except possibly at A. So what I'm saying here is the function f need not be defined at A. Right? So the function is defined on the open interval containing something on the left of A up to something on the right of A. And at the point A itself, this point A need not be included, right? So the function is defined both on the left and on the right of A. Now to say that the value L is the limit, what we meant is this function will go very, very close to L. Remember in the earlier example, our L was like 2. This function will go very, very close to the value L as x goes very, very close Be very careful, very close to A but not equal to A. Right? It's important to note that when we say x is approaching A, this word approaching A means it goes very close to A but it is not equal to A. And then if that is the case, we say that the number L is the limit of the function fx as x approaches A. And in formal writing, this is how we write limit as x approaches A of fx is equals to L. In the other example, if you could recall, we had limit x approaches 1 of fx is equals to 2. Okay, so with this formal statement put in place, let's now look at some simple example. Now, in example 2, you are asked, what do you think is the value of this limit? Now, to think through and to work out a value for this limit, what you can do is you look at this function. Obviously, at the point x to 16, this function is undefined because you're going to come up with a 0 over 0. So it's definitely an undefined quantity. Nevertheless, we can still study how the function, or we can think how the function will behave when x goes very close to 16. So one way to go about it is, you can actually first and foremost tidy up this expression using a simple arithmetic. For the denominator, I have actually factorized it. And as long as x is not 16, which means I will never have a 0 over 0, because if x is not 16, you will never have a 0 over 0. I can then cancel these two away. Upon cancelling these two away, I'm left with only just like this. So if a function is just like this, as long as x is not 16, and then when it goes very, very close to 16, you can actually kind of, imagine that if this number is very, very close to 16, then the square root is kind of very, very close to 4 and end up with the number 1 over 8. And therefore, you can then quite easily guess that the limit of this function is actually 1 over 8. Now that we have seen a very simple example in example 2, how we can actually sort of evaluate the limit of a function, we want to now learn more ways or equip ourselves with more tools that we can actually calculate or evaluate the limit of a function. And to do this right, we want to start off first and foremost with some standard results. Here we have what is called result A. We call it result A. Result A says if this is a constant, the limit as x approaches A, and this is a constant, right? It's just a constant. This statement can be used without proof. It means if this is unchanging, imagine this is unchanging, right? So no matter how x changes, as x approaches A, this value of the function maintains as C. That's why this statement holds true. That no matter how x changes, as it approaches A, the value of the function remains at C throughout. Next, if your function is just x, then the limit as x approaches A is just A. Obvious, right? Because imagine if this is very, very close to 5, obviously this number will be very close to 5. So if this x approaches A or goes very close to A, so this number x will therefore be as good as A. And then in the case of sine x, in the case of cos x, in the case of exponential or ex, you'll find that these three statements can be used without proof. These are like so-called basic results. You can just use them without proof. And then you have another one, the limit when x approaches A. But for this case, there is something you need to note, that this value A must be positive. Because if you could recall, right, ln of a function requires this value here to be positive. So that's why you're going to impose condition that x approaches a positive number. So if x approaches a positive number, what we're saying here is then ln x will go very, very close to just ln A. And then now for the same reason, we have also x more than 0 because it's a square root. When x approaches A for square root of x, you find that it approaches just root A. So with this basic and simple results, we can try to actually work out these 6 limits. Okay, give yourself that 1 or 2 minutes to try. So for the first one, based on the earlier result, because this is a constant, so the limit of this function is just a constant 4. If this is simply x, then as x approaches 2, the limit will also be 2. Likewise, I can just plug it in. Sine of pi over 6, you expect this thing to approach the value of, what is sine of pi over 6? Sine of pi over 6 is like 30 degrees. Sine of 30 degrees, if you could recall, is just half, and so on. So if you were to do your arithmetic for example 3, it will turn out to be A, B, C. Oops, let me just adjust this a bit. Okay, part A, part B, part C, and then D and E and F. And you realize very soon that in this simple example, it is somewhat like as good as plugging in the value 2 into here, or the value pi over 6 into here, or the value pi over 4 into the x here, or the value of this thing into this, and so on, In the case of part E, I want you to note for part E, right? When you plug it in ln 5, E ln 5, right? E ln of anything, right? It's just that thing itself. This is something from basic arithmetic you learned in the earlier years. Right? And then for this ln E squared, the 2 can be brought to the front, become 2 ln E, and ln is 1, so you just left 2. So I find that in these simple examples, it is as good as just putting in the value of x into all these functions. And it's somewhat true. Right? That's why they're basic results they can use without proof. To help us with calculating many more limits, we have to then equip ourselves with more standard results, in this case from Theorem 1.1. Now these are also standard results that even if I have not told you, you could potentially have guessed it. In the first one is the constant. If this is a constant, it can be pulled out. And the second one is if you have the sum or difference, again it will be the sum and difference of the two limits. Likewise and likewise. Now these results look easy and quite intuitive, but there is a catch here, that these statements can only hold true if the limit of fx and the limit of gx separately, these two limits separately, they exist. Let me say there is a value for this limit, in this case called L, and there's a value for this limit which we call M. So these two limits must first and foremost exist. Then only it can break them out into the sum and difference, or the product, or the division. If any of these limits do not exist, then these results will not be true. Alright? In particular for part D, even if this limit holds true, it means there's such a value for this limit, you must make sure that this limit, or the M, right, you can see M, right, this is the limit of gx, this limit mustn't be 0 in order for this expression to be meaningful. Because if this were to be 0, then you got something over 0 which is therefore undefined, and when that happens, you can't actually use this theorem. So with this, let us try to compute more limits by using these results and the earlier standard result in result A. Like in the case of example 4, right, you can actually use this part A result, which allows you to pull out the number 13, the constant, and then you're left with 13 limit x goes to 5 of x. And remember, in the result A, I can just replace the x with 5. You see, I took out the 13 and I simply replace x with 5, and I get the answer of 65. For the second one, right, limit as x goes to 5 of x plus 2, I can actually use the idea of the sum and the difference of limits. Right, again, the difference of limits. So let's see, okay. So for part A, I could just broken them down into the sum of two limits, and this one being a constant, it remains as 2. This is just x, it becomes just 5 in the result A. And then likewise for part B, you can break them up into two limits, and individually you compute the limits, and then you get this answer. And likewise for part C, I can first and foremost break them out into two limits, and then take out the constant 2 from the result that we saw in Theorem 1.1 part 1. You can see whenever it gets a constant, you can just put a constant. So then these three limits in example 5 can be computed quite readily. Of course, you may say, hey, Mr. Lim, I could have just found all these limits without having to use Theorem 1.1. I could just potentially plug them in like what I did in the case of result A. It's somewhat true. It's somewhat true. But if you are trying to be very careful and use the theorem in 1.1, then these are actually the steps. And for this simple question, even if you were to do it by just putting 5 right away and therefore give 7, or putting pi over 4 right away into this 2 and give you a 0, I'm also okay. Bear in mind, these are simple examples to just illustrate to you that these theorems are used that way. Because in more complicated examples or sums, you will really have to use these theorems to help you to break down into the sum or the difference of two limits, or the product of two limits, or the quotient of two limits. Moving forward, let us look at more examples in example 6. In part A, you have the limit of x ln x. You can use a theorem 1.1 to break this up into the product of two limits. Evaluating the first, I get 2, and evaluating the second, I get ln 2. And this gives you the result for part A. In the case of part B, if you have a quotient, this is broken down into the limit of the numerator over the limit of the denominator. I want you to note that for the numerator, when I say x tends towards 1 of cos x, and I got cos 1, I want you to bear in mind that this 1 refers to 1 radian. In this case, it works in breaking up this into the limit of the numerator and the limit of the denominator, all because in this case the limit of the denominator doesn't go to 0. That's why this calculation works. Likewise, in the case of part C, you have the limit of sine x over cos x. Like the earlier part, I can break this up into the limit of the numerator over the limit of the denominator, and I can calculate the numerator separately from the denominator. And once again, because this is non-zero, this calculation actually works, and it works to a value of just 1. Now we want to introduce to you some other important results. In part 1 of result B, it says if the function fx is a polynomial. Now you want to know that polynomial is quite special. It is something like a0 plus a1x plus a2x squared plus a3x cubed, and so on and so forth. So it's actually a function of x to the power of n, where the power n is a positive integer. So what the statement says, if this is a polynomial, then the limit of this polynomial is just the value of the polynomial at the limiting value a, when x goes towards a. If you have a rational function, what is a rational function? A rational function is actually a function where you have a polynomial over a polynomial. So if gx is a polynomial over a polynomial, what the statement says is to calculate the limit of gx, it is the same as evaluating the value of g at the point a. So over here, it gives you some idea how this can be easily proven. So you can read these few lines to actually give yourself a gut feel why these results hold true readily. Let's look at example 7. Okay, in example 7, it is actually the case of using what you have in part 1 and part 2 of result B. Now, in example 7, this is a polynomial, right? As a polynomial, like what we say in the earlier result B part 1, if this is a polynomial, evaluating this limit can be found by just putting x as 2 into this, and resulting in just 2 squared minus 2 or equals 2. This is a typical example of what is called a rational function. I want you to note that the numerator is a polynomial and the denominator is also a polynomial. So by the earlier discussion in the result B part 2, if you have a rational function, again to calculate the limit of this rational function is to put in x as 2 into the numerator and the denominator, and then you can evaluate the limit for this case as 5. So what you have here is simple examples on evaluating the limit of a polynomial and the limit of a rational function. In particular, I want you to note this part B, example part B. In this particular example, things all worked out well. What if you have the case where both the numerator and the denominator will go towards 0 when x approaches a certain value? When that happens, of course, these simple techniques won't work anymore. So when that happens, potentially we have to resort to the use of other techniques. One of them is the use of factorization, and later on we're going to look at how we can use conjugate search to help us. So let's look at example 8. In the case of example 8, this again is a rational function. Unlike 7b, if I let x go towards 2, you find that the numerator is 0, and likewise the denominator is also 0. So when that happens, you cannot just evaluate the limit the way we did in example 7b. So what we can do here is we can actually try to factorize the numerator into this. Now, as x tends towards 2, you want to bear in mind that when x tends towards 2, x is never 2. And therefore, this number is never 0, and this number is also never 0. And therefore, we can just cancel off this x minus 2 away, leaving you with just x plus 2. So that when x goes towards 2, I can then just evaluate this number as just 4. Right? Likewise, in this example, you have the same problem. If you put x as 3 to the numerator, you get 0. If you put x as 3 to the denominator, you again get 0. So when that happens, so one possible way is to use factorization. So upon factorizing, I get this expression. As x goes with 3, because x is never 3, this cancellation makes sense, and you're left with x over x minus 1, which you can then evaluate this limit by putting x as 3 to the numerator and then the denominator separately. You get the answer of 3 over 2. Right? How about the other kind of cases? So if you have case like this, right? One way of resolving a limit that involves a fraction that's like this. I don't bear in mind that in this case, this fraction is not deemed to be a rational function. While this is a polynomial, the denominator is not. So this is not a rational function. In any case, when x goes towards 1, this will go towards 0, and this will also go towards 0. So when that happens, one possibility of resolving such a limit is to use what is called the conjugates. Root x minus 1 has a conjugate of root x plus 1. So what you can do is you can multiply this to the top and bottom, and resulting in this expression. Now, as long as x is not 1, these two numbers can be cancelled off. I'm left with root x plus 1. And then now to evaluate this limit, this is now replaced as just root x plus 1, so that when x goes towards 1, I get 1 plus 1, which is 2. Look at more examples in the use of conjugates. In example 9, you again have a fraction. When x goes to 1, this will be 0 and this will be 0. And like the earlier example, I can resolve this by multiplying by the conjugate, you can see. And then upon expanding, I can cancel these two by introducing a minus 1. Right? Upon cancelling these two, you will have a minus 1. And then when x goes towards 1, you in the end will get just minus half. For case of part B, 9b, right? 9b, you also has a fraction over a fraction, and when x goes towards 2, you find that the numerator will be 0 and the denominator will be 0. So once again, we are going to make use of the conjugates. So what I'm going to do is I'm going to multiply the conjugate of the numerator, which is 2 plus root 2 plus x, both to the top and the bottom. Upon expanding, right, I will have this nice expression that can cancel off with, okay, if you open this up, this will give you 2 minus x. So I can cancel it with x minus 2, leaving you with a minus 1. And then when this is cancelled off already, you find that when x goes towards 2, the numerator will not be 0, neither will the denominator be 0, and therefore I can evaluate this limit quite quickly by putting x as 2 inside the denominator. And then I'm get the answer of minus 1 over 16. Okay, so up to here we have evaluated different limits using some of the methods. Some are quite easy and some make use of Theorem 1.1, and then now we have the use of factorization, and we also have the use of conjugates. Now following this, we are going to learn more powerful techniques to evaluate limits. To start off with, we are going to learn about this thing called the squeeze theorem. These are even more powerful results where the earlier methods you have learned will be hard to use to evaluate some of the more complicated limits. So we can use the more powerful results such as the squeeze theorem. In the case of the squeeze theorem, it says if you have a function that is sandwiched by two others throughout the interval, except for the point in question, if a function is sandwiched by two functions for the interval I, and if the limit of gx, the lower bound, and the limit of f, and the limit of the upper bound hx, if the limit of both the gx and hx, the lower bound and upper bound, have the same limit, then this theorem says the function in the center will also take on the same limit. So what happened is this function fx is actually squeezed by two other functions gx and hx. So if these two tend towards L as x tends towards A, what it says here is the middle one will also be squeezed to take on the same limit. And for a reason it's called the squeeze theorem, or sometimes called the sandwich theorem, for this intuitive picture that you see here, that this function is squeezed between these two, or you can say that this function is actually sandwiched by these two. Right, it's a very interesting theorem that can help us to calculate the limit of more complicated function. Let us start with this. So now in this question, you're asked to show that the limit of this is 0. Now in this question, I want you to note first and foremost that you can't break this into limit of x squared and the limit of sine 1 over x. Why is it so? Because in order to break into two limits, you must be sure that the limit of x squared as x goes to 0 and the limit of sine of 1 over x as x goes to 0, both of them exist. But in this case, you have no way to ascertain that the limit of sine 1 over x exists. So for a reason, you can't just break into the product of two limits. So therefore, those earlier theorems or those earlier results do not work for this particular question. So one way out for this is you can actually use so-called the squeeze theorem by first noting that this function sine of 1 over x, no matter what 1 over x is, this function is always sandwiched between minus 1 and 1. And because of this, then x squared sine of 1 over x will be sandwiched between minus x squared and x squared. Right? For all the value of x except potentially at 0, because at 0 we are not sure. Right? But it doesn't matter. Then what you know is for minus x squared, when x goes with 0, and for x squared, when x goes to 0, you find that both of them, both the limit of this function on the left and this function on the right, both of them will go towards 0. And when that happens, squeeze theorem say even the central function will also be squeezed towards 0. So by the simple use of the squeeze theorem, we are able to evaluate the limit of this somewhat complicated function that the earlier results and theorems cannot help you. Geometrically, if you were to plot this graph of x squared sine of 1 over x will look somewhat like this. So from the graph, you can see that it's true. When x goes with 0, the function x squared sine of 1 over x does go towards 0. Can you see? When x goes with 0 from the left and from the right, the function value or the y value is almost 0. or rather it goes with 0. So this is a very interesting result called the squeeze theorem. Right. Okay, so this is a remark that I've just told you about. This remark is to stress to you that you cannot actually use those results in the earlier theorem. There is another result that's quite nice. Is given this in this exercise. In this exercise, you are given that sine x over x. This is a given result. This result is not hard to prove geometrically, but anyway, assuming that this result is given to you, that sine x over x is sandwiched by these two numbers, then what happens is I can calculate the limit when x goes with 0 of cosine x, and I calculate the limit of this as cos 0, and therefore is 1. So because the limit of the left, which is the limit of this left function cos x is 1, and the right hand side is always 1, right? Or you can, if you really insist, you can say the limit when x goes with 0 of this function is also 1. So because the limit of the left and the limit of the right as x goes with 0 is the same, which is in this case 1, by the squeeze theorem, we can then say that the middle function, which is sin x over x, will also go towards 1. So by a very nice or simple application of the squeeze theorem, we have this very nice result that limit as x goes with 0 of sin x over x is equals to 1. By the way, if I turn this upside down, it means I write this as x over sin x. The limit will also be equal to 1. It's the same. Okay, let's look at this important result again. Alright, earlier on we have already discussed this important result by first assuming the inequality, this inequality, right? Okay, how does this inequality comes about? Actually, it is given in this diagram. Okay, in this diagram, it is an attempt to show you how you can obtain a certain inequality that allows you to come to this conclusion via the squeeze theorem. So what happened here is in this diagram, which is taken from here, right? The area of this triangle is half times base times height. This is actually a unit circle, and from this circle you draw a triangle like this. So obviously this triangle has an area of half times base times height. The height is tangent x because opposite over adjacent is tangent of this angle. So the area of this triangle is tangent x over 2, and the area of the sector, which is this, we all know is half r squared theta, half times r, which is 1, times r, which is 1, then x, half r squared theta. Remember, half r squared theta, the formula that we know to find the area of a sector, half r squared theta. So they give me half times 1 times 1 times x, and therefore it's just x over 2. And lastly, you can find the area of this triangle, which is of course smaller than this, using half a b sine x. Half a b sine x will end up with this expression, half a b sine x. So from this geometrical consideration, you can see that this result holds true quite readily. This triangle is having a bigger area than the sector, and this sector has a bigger area than the next triangle. So we have this statement that half tangent x is more than half x is more than half sine x. So what happened is, if you were to times throughout by 2 over sine x throughout this expression, you will end up with this. Now you look at this one, and you look at the earlier one, it's quite similar. Right? They're quite similar. It's just a reciprocal of the earlier one, right? Okay. So with this result, which is quite similar to the much earlier one, I can again, if I want to, take the reciprocal to obtain this result that you used in the earlier example to show that the limit as x goes with 0 of the middle term is equals to 1 with the use of the squeeze theorem. So this inequality that you got here was actually used in this example. And by the use of squeeze theorem, we have established this very important result. From henceforth, you can just use this result without proof. and you want to study the proof again, you just go through this page, which is found on page 9 of your notes. Right. So with this in mind, let's try some example on the use of this important result. In example 11, if you have to find this limit, you can break this up into sine x divided by cosine x, which is tangent x. So you can break it up into sine x over x and divide by cos x. So by the earlier theorem, if you have a division, right, I can break it up into the limit of the numerator divided by the limit of the denominator. And this is applicable because the denominator doesn't have a zero limit. I mean to say when x goes to 0, right, cos x doesn't go towards 0, so it's okay to use that theorem. So by using a theorem, I can then say that I can break this into the limit of the numerator divided by the limit of the denominator. And this one, based on the special result we had earlier, this is just 1. And this is also 1, and the answer is just 1. Let's look at the next example, B, okay? Sine 2x over sine 3x. How do you evaluate sine 2x over sine 3x? Okay, there is some result here you can read slowly for yourself, but let me just go straight into the example. To find the limit of such a function, right, what you can do is you can introduce, you can rewrite this thing as sine 2x over x, sine 3x over x, right? This fraction and this entire thing is identical, there's no change, right? There's no change. I've just introduced a division by x. And then what happens is you can break this into two limits. And now that you got this line, right, you got limit of sine 2x over x. What I can do is you can put 2 here, become 2x, and therefore I put a 2 outside here. You can put a 3 here, so that it becomes 3x, and you can put a 3, balance your 3 outside here. So if you have a 2 here, and a 3 here, and you got 2x here, and a 3x here, right? So this expression will look like sine 2x over 2x. So based on that standard result that we had just now, sine of one angle over itself, when the value goes to 0, right, is just 1. Bear in mind there's a 2, otherwise there's a 3 here. So this limit, and this limit, right, by just introducing a 2 here and a 2 outside here, and a 3 here and a 3 here, I conclude that the limit of this will just be 2. Right? It may look difficult, but if you want to understand, if you find it hard to understand, you can actually look at this one first. So this result, in trying to compute the limit of this function, what happened is you introduce a p here. You can see, introduce a p here and put a p outside, and this limit is just 1. Right? This limit is just simply 1. Right? Sine of the angle over the same thing, right? When x goes to 0, when x goes to 0, px also will go to 0. It's the same. So that's why this limit will just be 1. Right? And with this, we have come to the end of page 10, and this is where our e-learning lesson will stop.